In this episode, we're going to take a look at the Pecron E1500LFP portable power station. We're going to do a full load test, load it up to its maximum power, see how long it'll run, do a full charge, tear it down, take a look at the build quality, take a look at the batteries, and take a look at the waveform. I think you'll find this one a bit interesting. Don't know how long it'll go. We'll try to keep things moving along here. Let's take a look at it. Well, today we're going to unbox and check out the Pecron E1500LFP power station. So let's see what's in the box. We'll open it together. I tell you, I got more of these things around here than I know what to do with. Okay. In the box we have the accessory kit and the unit itself. So let me get this thing unboxed off the bench and we'll take a look at it. Still factory sealed. We're going to open this unit up, go over the features. I'll give it a full charge, we'll give it a load charge, see what we can do to load this thing down, how long things will run, and so forth. But before I do that, let's take a look at some of the features this one's got. On the left side, we see a DC 48 volt battery extension. So it'd be an optional battery with a cable that would connect multiple units together. That's what that's for. On the right side, there's nothing. Everything else is on the front. On the front, we have our main fuse, and it says 100 to 120 volts, 15 amps maximum. This is for your AC input. Your cord plugs in there. You also have DC inputs on the front here. You have two inputs. You have an input 12 volts to 18 volts, 100 watts maximum. That's for charging it from your car. And then this one here, 32 to 95 volts, 700 watts maximum. Well, obviously, that's going to be to plug into a solar panel to charge it up. On the output side, we have a 12 amp, 30 amp maximum output. Over here, a 12 volt, 5 amp maximum output, and a 12 volt, 10 amp cigar lighter type. We also have 4 USB-A 18 watt outputs, a USB-C 18 watt, and a USB-C 100 watt output, and 3 AC outlets with output maximum power of 2200 watts. There's also wireless charging on top for your phone. If I turn the unit on by either pressing the DC or the AC buttons, press and hold, that turns on the DC output. Looks like the battery is at 68% charge. Press and hold to turn it off. Press and hold the AC, that turns on the power. Again, it's enough power for 34.6 hours because we're not drawing anything right now. First things first, I'm going to charge the unit and we'll get it charged up, and then I'll do a rundown on this. We'll run it down, and then if we can open this up, I'm going to open it. So I'm going to grab the main power cord, we'll get this plugged in and get it charging. Should also point out that there is wireless charging built in, and it tells you how to turn it on and off here. You can also connect to it by Wi-Fi, it looks like. It says press and hold the AC button to turn on and off the AC output. Press and hold the DC button to turn on and off the 12 volt USB and wireless charger. If you press and hold AC and DC at the same time, you'll reset the Wi-Fi and enter the pairing mode so you can pair it with your phone. This basically generates a hotspot. And it says if you want to store it, just charge it to 30% and then recharge it to 60 every 3 months to preserve the battery. And of course, if you want to use solar charging, follow the instructions with them. In the accessory pack, you should find some charging cables here. And we do. Oh, what do we have here? Well, isn't that kind of neat? It has this is for charging up, like to give your car battery a jump start. So you can plug in the front here. This is the 30 amp maximum output, and attach these to your car battery to give your battery a bit of a jump start so you can start your car. And it's going to have a big maxi fuse in here for sure. There it is, 30 amp fuse. So if you were to short these together, you're going to pop that fuse. But that's that. 30 amps. I was not expecting that. Here's the charging cable comes with it for charging from solar, and another one here for, I guess this is for, is that, no, that's for a different type of solar. That's for a different solar panel. Different outputs, right? Some solar chargers will have a combined, I forget the name of that connector because I don't do anything with solar. And then of course these ones are your conventional solar connectors that you connect to the panel, and that will plug into the front here. Also have a 12 to 18 volt charge cord for charging it in the car, and of course the 120 volt heavy duty 15 amp cable. We're going to plug this one in and get this unit charging. And you'll see that it is going to charge at 1250 watts approximately. We're going to let it charge up, get to a full charge. It says it should be charged up in, well, what, 20 minutes or so? Fans are spooling up. We're going to let this thing charge. Then I'm going to load it down and see how much I can load it down before it shuts down. We'll run the battery rate down, time it, and we'll pop it apart and take a look inside. What I don't know on this is whether it has a UPS. I guess we can find that out pretty quick if I turn on the power while it's charging. So my AC power is now on. Let me grab something I can plug into here, like a heat gun, just because the heat gun is so convenient, and I can run it at low power. Okay, so I'll put it on low power. Drawing about 600 watts. I'm curious, is it a standby power supply? Or is it a UPS? I'll unplug the power and see what happens. It's a UPS. Put it back in. Started charging again. Now what if I'm drawing full power? I'm still able to put some charge in. I'm drawing 1300 watts, and I'm still charging the battery. So this is operating now as a full UPS. If I unplug the power, it's 1400 watts on here. You can hear the motor change when it switches over to power. Yeah, UPS, got a light here. So this will operate as a full UPS. Oh, I'm happy. I may have to take this inside and use this as a UPS. A little bigger than the one I'm using right now. But lots of power, that's for sure. But there you go, you can use it as a full UPS. So right there, UPS. And even drawing 1500 watts. 273 going into the battery. If I shut this off, now the power drops to 0. The charge power will go back up now, because it is a maximum 15 amps that it draws on the input from AC, and up to 700 watts off of the solar panel if you've got a big solar panel on it. So we'll let this fully charge. I'm going to load it up, see if I can break it. Turn on the DC power. DC output is now on. And if I take my phone and just drop it on top, my phone goes into charge. So this is our specifications. It's the model E1500LFP. The battery capacity is 1536 watt hours. It's a 51.2 volt battery, 30 amp hour. AC output is 2200 watts maximum, 100 to 120 volts. It has 3 outputs, 4 USB-A. It'll run at 5 volts, 3 amps, 9 volts, 2 amps, 12 volts, 1.5 amps for the USB-A outputs. One USB-C will also run up to 18 watts maximum. And the other USB-C, its output is 5 volts at 3 amps, 9 volts at 2 amps, 12 volts at 1.5 amps, and 20 volts, 5 amps maximum, so 100 watts. DC output 13.6 volts, 30 amps. Wireless charging 5 to 12 volts, 15 watts maximum. Your AC input wattage is 1400 watts, that's the charging power. Input voltage 100 to 120 volts. UPS power 1800 watts at 120 volts maximum. DC charging 12 to 18 volts, 100 watts, and 32 to 95 volts, 700 watts maximum. So this will operate at as a UPS for 1800 watts, an 1800 watt UPS. That's pretty beefy, that one. And of course there is a user manual. It was just tucked in with the accessories. So it just goes over what I've already gone over, what the ports are, and it has our specifications on here. Rated at 2200 watts, but I want to see what the surge is on this. It should tell me what the surge is. Because when the UPS, when the power station has AC and the AC output is turned on, the UPS will be automatically turned on, and the UPS icon will be on to indicate that this is on to remind you. So from the recharge time, it says from the wall, about 1.8 hours to recharge the battery. From a generator, about 1.8 hours. And here's our solar charging time. If you have solar, a 200 watt panel, you'll get to 8 to 9 hours, or 9 to 10 hours to recharge. If you have a 400 watt power panel, 5 to 6 hours, and if you've got 600 watts, then 3.5 to 4 hours. Of course, it's going to be dependent on the amount of sun that you've got, right? So that is that. And you can switch the AC output frequency between 50 and 60 hertz. Here's our UPS function. It says the UPS function can provide loads such as computers, data centers, telecommunication equipment, near instantaneous 8 to 20 milliseconds protection from uninterrupted power interruptions for the main supply. It says not applicable to specific applications that need a transfer time under 8 milliseconds. So in other words, it's not running as on the inverter at all times, like some of them do. My other one that I'm using, for example, it runs on the inverter full time, and then the AC just keeps the battery charged. I believe the other Pecron that I reviewed before, it works the same. You're always using the inverter because it doesn't have an AC power cord going into it. You have to plug a power brick in, and it charges with like a 48 volt charger. So it's always running on the inverter. That will operate without any type of delay. This is near 8 to 20 milliseconds, so it's pretty short time. Wait, long press both of them together, and then I long press the DC. Oh, might help if I turn on the AC. I gotta turn the AC on to do this. AC on, okay. And then long press the DC. Okay, so 60 hertz or 50 hertz. That's how you select it. And then you press it again. It's 120 volts or 100 volts, 110, 120, right? So you can switch your output. And then the next one is how long it'll run before it automatically shuts off under no load. And so that if you unplug something, you leave it turned on, it will shut off if it's not being used. And then it says press the AC button, and so our settings, first one 60 hertz, second one's voltage, third one is the default, which means the machine without any settings for auto shutdown. So in other words, when it's set to off, it will just stay on until you turn it off. That's the other one's important if you're using this, if you're camping or something, right? You don't want to leave it turned on all night by accident and wind up with the battery being dead in the morning. So you can set it to shut down. That way, if you forget to turn it off, it'll shut itself down. Setting 4 is to reset the Wi-Fi, and of course you can use the app, which I never use the app because I don't think that you should have to, and you don't. The app is only going to be to do a few things. Control the device and make personalized settings. And you can just connect it to Wi-Fi. You press both buttons and it'll go into Wi-Fi mode. You can cascade 2 additional EP3000 48-volt plus battery packs. It's strictly forbidden to use non-Pecron battery packs. You can use an E1500LFP with one solar panel, or you can connect it this way, and you can also connect multiple solar panels together, which will increase your voltage. It says for using the solar panel, the VOC of a single solar panel should be less than 48 volts. That's the voltage open connection, right? If you measure with a meter with no load, it should be less than 48 volts of a single solar panel. Because if you put 2 of them together, that would give you 96 volts under no load, and that would be over the maximum, which is 95 volts. So a single panel should not be more than 48 volts. 2 of them together, you have 96 volts. That's your absolute maximum under no load. And it shows you here you can actually connect. This one's connecting the solar panels in parallel. And you can connect them in parallel or in series. It tells you here, don't do it this way, right? You see? You connect 3 solar panels in parallel, but don't do 3 of them in series, because the port only works with 32 to 95 volts. Open circuit voltage exceeding 95 volts would damage the panel. If you've got 2 32 volt panels in series under no load, that would exceed 96 volts. So there's a big warning there not to run them in series. It's a lithium iron phosphate 4 battery. It can retain 80% its original capacity for about 3,500 complete charge cycles. Here's an important one. It does use the UL certified automotive lithium iron phosphate battery pack. Here we are at 99%. So this thing's going to stop charging momentarily, and then we're going to do a big discharge. Before I finish my complete charge, let's just see what happens if I turn on. I'll get my charge up to full here momentarily, but drawing 1,300 watts, 1,200 watts now. It's going to run for an hour and a bit. Let's turn on the heat gun in low power. We'll see what type of a load we can get. So we're at about 1,800 watts now. I'm sure if I kick this into high power, this thing's going to go into shutdown. I just want to find out. Yep, because we went over 2,500 watts. So went into protection. Overload. Wonderful. Probably turn it back on here. Take my load away. What do I do to get out of an overload condition? Turn it off and probably turn it back on. There we go. That's how you get out of an overload condition. Alright, I'm going to just finish charging the battery. And then what I'm going to do is I'm going to run the heat gun on low and run this heater. That'll give us up to about 1,800 watts, and we'll run it at that. I guess if I wanted to get creative, I could plug a TV into it as well and take it up higher, but I think running 1,800 watts is probably going to be a pretty good test. So we'll just give this another couple minutes here to finish its charge. One thing I noticed while it's charging, because it is a UPS, it is a standby supply. So this is actually my AC incoming. AC is 117 volts right now, because I'm not going through the Variac or anything. It's plugged straight in. So I got 117 volts at my outlet now. If I unplug this, it'll switch to battery, and that'll go up to 120. You see what I mean? Plug it back in. I got 123 volts there until it starts to load. Once it loads down, the voltage is dropping a bit. Now that might be because I'm going through, this is plugged into my little kilowatt power meter. So Might be a bit of loss there, or just the voltage is dropping a bit because I am under load. We're at a full charge. I get my stopwatch going here on my phone, turn on the power, start this running, and we'll turn on the heat gun on low power. So now combined we're drawing 1738 watts. This should help if I unplug that. Now we're drawing power from the battery completely, and it says it's going to run for a little over half an hour. It's not even going to run for an hour. What, 40 minutes or so? We'll see. But at full power, I mean, we're drawing almost maximum power. Output is 2200 watts, so I could add some more stuff to here and really load it down. Plug a TV in, a plasma TV. Our draw will go up a bit now that I've put on a television as well. Get a picture going on it. Alright, now we are running a 43-inch plasma TV. We've got two heaters going here. I've got my heat gun going, and I got this heater going over here, and I've got this television, 1970 watts right now. So we're pretty much loading this thing down to full power. We'll just let this thing run, and we'll see how long it goes before it shuts down. This is one of my free plasma sets I got. Works pretty good. I'm going to turn on the DC power as well and get my wireless charging going. I'm only getting 4 watts right now through the wireless charger. There we go. That's kicking up. See, load this thing right down. So I've been in about almost 7 minutes now. It says half an hour remaining. We're at 85% capacity. Battery is discharging quite nicely. Coming up to 20 minutes and we're at 53% charge. It says 0.3 hours remaining. Put on a hockey game because the white ice will make the plasma draw more power. Still sitting at about 1966 or so watts. Going 26 minutes now. 0.2 hours left, 38%. So I'm in almost 32 minutes now, 24% battery life remaining. And it's been, say, going now for about 32 minutes at full power. 35 minutes in, we're still at 15%. Down 13% now. I don't know how low it'll go before it shuts off. We're going 36 minutes. We're at 2% now, 40 minutes in, 40 minutes and 35 seconds, down to 2%. So this should be shutting down pretty quick here. That's not bad considering the amount of power I'm drawing from here. 1923 watts at the moment. But it's up as high as like 1970 depending on what's on the screen of the TV. Right now they're not showing ice. It should be shutting down anytime now. We're at 1%. And there it went. 42 minutes on the button. That's respectable. The fan, of course, is going to continue to run for a while to cool things down. Oh, there it goes. It's right off now. So, next, we're going to rip this thing apart. Hopefully this has got Phillips screws in it. Remove some of the plugs. And we'll just start zipping out screws. And hopefully this one's going to fall apart. Also have to lift up these end caps as there are more bolts down the side here. These ones being hex keys. So we'll remove these 4mm hex bolts. These are kind of beefy. Okay, I wonder if it'll... Oh, there we go. Well, that's simple enough. Now, we'll just remove the power cord here for the wireless charger. It's glued in place. We gotta remove that. I need that out of the way to inspect this unit if we want to inspect it the way I want to inspect it, and that is tear it right down. They're and it's goes in that way. so they don't get jostled loose. It's actually got quite a fair bit of weight to this. The circuitry for the wireless charging is right there on board. Alright, let's take a look at what we've got here. We've got lots of circuitry on this one. This board obviously is the DC board, or maybe it's charging. I think this is probably the DC board. Could be charging as well, I guess. It's got its own fan on this heatsink. But looking at where these cables go, this looks to be the DC output. So this is all DC. The AC board is going to be the one down below here, the one that we want to get to. So we'll pop out a few more screws and see if we can lift out this heatsink. So we just lift this up here and swing this out of the way. Thermal pads from the lower heat sinks to dissipate through this one. And I wonder if I can get this out of the way without having to disconnect anything. I probably should unplug a few things. It's just that all these connectors, they all appear to be glued in place. Can I unplug these? Yep, I can unplug those. Alright. Well, that wasn't supposed to happen. I just took the whole plug apart. The header's still on here. I guess we can put that back on later. Just push the plug down through the holes, but that's what happens when you glue things on. There's our big heatsink with our thermal transfer. We'll take a look at the AC inverter board, which is this one. I believe we can also probably lift this one off and get a look at the batteries down below. I can't disconnect the power because of how they're connected. I don't think I can even see them, but we don't need to, because I can lift this out of the way enough so you can see that beautiful battery pack. Wow, look at the size of these cables that are connecting. They're silicone insulated, by the way, but look at the batteries on this thing. Data production 12/12/2023. So this battery pack is exactly 60 years younger than my wife, because her birthday was December 12, 1963. So I can say, hey, this thing was built on your birthday. Alright, so what do we got here for cells? Thermal management. There's heat sensors on here to monitor the temperature of the cells, and they are warm, and I would expect them to be warm because I just put these things through one mother of a discharge cycle. What are these cells? Can I get a close-up of the batteries on here so we can see some numbers? You guys can probably read them better than me. Can we see the battery numbers? Maybe over on this one over here. I can see some numbers in here somewhere. It's a 32140. That's the battery. 48 watt hours, 3.2 volts. But the cells themselves are beautiful. Over on the right side here, this is our battery management over here for our cell balancing and battery management. Look at the size of the lugs on here. We're talking some pretty serious current. This is a metal plate here. So there's a bus bar on this side here, and there's another bus bar here. This is our power input right there. And then these cables take the power up to the inverter board. All the rest of these are part of the battery management system over here, which I say we're not gonna touch that. Put this over here a bit so we can get a better look at the battery management board on this side. Can we see it? Let me grab my other camera so we can get a close-up. Here's a good look at the battery management board. Get some light in there so you guys can see the components mounted in here. That's the connector for the secondary battery that would be connected right down here. That looks really well built. Fuses, a bunch of fuses here again. It's a 51.2 volt battery pack, 30 amp hour. That's the battery pack model number, or part number, I guess. E1500LFP-16S2P. That would be the part number for the replacement battery, which I would imagine would be probably sold as an entire, if it was available. I don't even know if it's available, but if it was available, that's probably sold just as one complete module. But you've got these massive cells in here. What's that count? 1, 2, 3, 4, 5. There's 10 there, and there's got to be some more. There's got to be another one down below. There's probably 20 cells in this thing, because I can count, right? 1, 2, 3, 4, 5 across here, 5 across here, and then I can see another row of them underneath there. So there's maybe 2 rows. There might be a second. This is quite deep, so there might be another battery pack. I'm not going to pull the batteries out, just because that would require me having to disconnect power and everything, and I just don't want to go through the hassle. I will put the meter across here so we can just measure what the discharged voltage is. It's 47.2 volts. And remember, this is discharged. This battery pack, when fully charged, would be, well, 51.2 is what they're saying, but we're discharged now. So that is to be expected. But there still would be a whack of power in here if you were to have a dead short across these. Yes, I can touch this. You don't get a shock with this kind of voltage, right? You're not going to feel 47 volts or 50 volts or even 52 volts. The skin resistance is high enough. You're not going to feel it. But if you were to short this with something metal, I guarantee you'd be welding it to the battery pack, and then bad things would probably happen with all these cells, because I don't know that there's a fuse on this part. The fusing all appears to be over here. There might be a maxi fuse on this bus bar. Anyway, that's a look at the actual battery compartment. Let's throw this thing back on before something bad happens. Okay, now we can look at the inverter. Keep in mind, this is the back, this is the front. Here's our control panel. Got plenty of fans on this unit. Got 2 fans over here to draw the air out. They're exhaust fans, so the fresh air comes in. If you notice the fins actually direct the air in so that the air flows around this way. With that other heat sink on top, it's going to draw the heat underneath, over top of the heat sinks here, and there's air baffles, as you can see. That's what this is. That's a baffle. That draws the air in and forces the air to go right over top of the heat sink. Then from there, after it passes over this heat sink, which is going to be cooling down, this is probably the inverter side, or the sine wave generator, then it's going to pass over the transformers and also get forced in through here, through these channels of air. There's another baffle over here that draws air around as the air is being drawn out. There's another baffle right there, which is sitting up against this heatsink. That's designed there so that it creates a vacuum on this side and actually draws the air in closer to the fins. So it might look like it's blocking the air. It actually isn't blocking the air. It's swirling the air that's coming in, and it's swirling the air around the heatsink. So what happens is the airflow comes in. Airflow will flow in through here. It starts to head this direction. This baffle will direct it into this side of the heatsink to draw off the maximum amount of heat on this side. Air will obviously also flow around the other side, which will then pass straight through here. Air that goes over here will hit this transformer and it will be baffled this direction around this heatsink. Air that's also coming around here will flow around and in behind this baffle. The vacuum created will draw the air in close to the heatsink to pull the heat away. Excessive heat that's forming on the top will then also be drawn through those thermal pads onto the top heatsink, which also has air flowing over it as well. So good cooling. So say when it was running, I didn't notice any hot air coming out. It wasn't even that warm. It was cool. It really has a pretty good cooling system. As you can see, all these plugs are glued together. So you're not going to have when this thing's being jostled around, because a unit like this is something that someone would usually take camping with them or have it in storage until they need it. So when it's being bounced around, you're not having plugs come undone, which is always a concern, and that's why they glue them in place. But construction-wise, this thing looks to be very well built. I'm going to guess that this is the actual step-up side. So this is the oscillator over here running at high frequency to generate the high DC voltage, which is then turned into 120 volts AC over here. I'm pretty sure this is going to be the sine wave generator. And here's our wires that go out. Our power coming in. The brown and the blue are the power inputs. These ones here, they go over to the yellow one over here is the ground wire. The brown and the blue right over here, AC power, one goes in through this fuse and then it comes back. Brown and blue are the line in, red and black, that's the output from the inverter. And these are going to be relays that switch between passing AC through and switching to the inverter, because this one being a standby UPS. So the inverter is not running when you're running off mains, it's running just off mains. This is ready to go, and I'm sure the inverter is running, it's just not switched on. So as soon as the power starts to drop, as soon as the AC main is interrupted, the relay will immediately energize and switch the power over, and it happens within that 8 and 20 milliseconds. It's quick. Anyway, insulation on the connections here, so no chance of short circuit. They've coated them all, and again, everything's glued in place. It looks great. So I think I'm going to put this one back together now, and then we're going to charge it up. I'll time the charging and see how long it takes to charge. We'll look at the DC board again as I'm putting it back in. So here's the DC board. Again, heat sinks that go on top of these heat transfer pads, I guess, that go on top of the heat sinks to drain away any heat that's building up, and just gives it overall better cooling. And then the cool air being drawn across the bottom of this, and then a separate cooling fan here for the DC side. So we'll grab this and put this back in place, and redo the connectors. That one started to come apart too when I tried to pull that one off. The glue is pretty good. Top cover should just go back on like that, and I'll start zipping in screws, and then we'll get this thing charging and time it and see how long it takes to charge up. Alright, got the unit back together. We're going to power it up and charge it up, and then we'll take a look at the waveform. There we go. So starting to charge. The fans will come on now and draw the air through here. And it's now charging at 514 watts. That should kick up a bit once it gets going. We'll start it says it's going to be 2.9 hours to charge. But that should actually drop once it gets going. So I'll start my stopwatch up and we'll just time it. The manual says about 1.8 hours once it gets going to full power, which is starting to, you can hear the fan starting to crank up now. To press the DC button while it's charging, and it'll tell you the battery voltage. So we're at 0% now. The batteries are sitting at 49.5 volts. Been running now for just over 6 minutes, and it's now kicked up. I just heard the fan speed increase. The battery voltage has now come up to 52.5, 52.6. And you can see the charging power wattage wise has gone from what, 500 odd watts to now 1343, and the time remaining has gone down to 1 hour. So we'll see whether it will actually fully charge in 1 hour. And I'm just doing a maintenance on some of the other ones that I've got in here, because I've got a few that have been sitting around for a while not charged. So you want to put a charge in. If you've got one of these units, if you're not using it, do plug it in once in a while and just give it a top-up charge, because the cells will self-discharge slightly, and if they get below a certain point, it is going to shut down and not start. And it says right in the manual, if you're not using it, charge it up, but every 3 months put it on charge for a few minutes just to bring it up to like an 80% charge, and store it at that. Charge it up when it gets down to 30 to 40%, and just keep topping it up once in a while. You don't have to do it often if you're not using it on a regular basis, a couple times a year, just to top it up. You just don't want the cells to sit unused for an extended period of time. Otherwise, you could end up doing what happened to one of mine here, which we'll probably do a teardown on and see how bad I screwed it by not charging it. It was sitting in a box for, I don't know, I think I reviewed it about 3 years ago, and it hasn't been charged since, and it won't charge. And we will take that one apart on a future video and see how bad it is. Hour and 15 minutes, we're at 99%. 54.2 volts is the battery now. Still charging at 586 watts, but it should be coming up to full charge anytime now. Okay, as the charge gets to full, we're at 99% now. Should be clicking over anytime. It's been going an hour and 37 minutes. Here's our AC coming out right from the hydro line, and I'll unplug the power and it will switch over to the inverter, just like that. And a little bit of slight bit of distortion here at the crossover point. We're not under any load. If I plug something in and put the system under load, let's plug a television in, turn it on. There, it's on now. TV is running. Here's our frequency is 60 hertz. Waveform looks okay. A little bit, it's not quite as clean as some of the others, but it's good. It's a sine wave. A little bit of distortion. A little bit of switching distortion here. I am running into not a very good load though. This is not a resistive load. We'll put the electric heater on as well and just see what happens to the waveform. Okay, turning on the heater. And as you can see, hasn't really changed much in terms of the waveform. It's not perfect, but it's fairly good. It's not like the old school type of unplug the TV, and it's still about the same. Shut off the heater. Seems to stay about the same. So that's how it looks on the scope. It's not bad. It's not perfect, but it's really not too bad. Again, I've seen others that have a little bit cleaner, a little bit of noise here on the waveform, as you can see. Maybe my probe isn't connected well. I guess it is. Anyway, that's it is what it is. It isn't perfect, but it's pretty good. I'll plug in the AC power. Watch it switch back to AC. And now it's switched back to hydropower. My scope can't seem to decide which phase it wants to log on to or lock onto. Huh. And then we'll go back to plug my TV back in. I'll remove the AC one more time, just so we can watch it switch. We'll go back to AC. So it's not as good as some of the others that I've seen, even from Pecron. The last one I looked at, their AC waveform, I think was almost dead on. This one here, a little bit of noise, but it certainly is more than adequate to run any of your devices. I'll put the link in the description. Say these ones here, these are not inexpensive. This unit here, I think I was looking at their website, it was about, on sale it was like $1,300. So these are not cheap units. This one retails at like $2,000. The second battery pack is almost as expensive as the unit itself. Again, you're paying for the batteries, right? That's what the cost is the batteries. Just for the hell of it, the TV that's plugged into it is drawing 172 watts. It's a plasma set. So much for the people saying that plasma sets were so energy hungry. If I unplug the AC, it's now running on battery. This TV will run for about 7.5 hours. A little over 7.5 hours right there. As the power consumption fluctuates a bit and it settles down. So you're looking at 8 hours, 170 watts. You can run 8 hours. When you're camping, if you've got this thing in your trailer, for example, you can run an LED TV for days probably. The modern smaller TVs are only going to draw maybe 50 or 60 watts, so you can run a lot of stuff off of this unit. Peak output power, 2200 watts. I ran it at just under 2000. Got it running pretty good there. Got it heating up good. And we didn't burn anything out. It still runs. Anyway, links in the description. Thanks for watching.